Okay, let's start the lecture. So today we discuss the extension of uniform continuous mappings. Theorem. So let's first state the theorem. Let X D1 be a metric space. Let X D1 be a metric space X D1 be a metric space and is a dense subset of X. A is a dense subset of X. It means a closure is equal to X. Okay, a closure is X. Now let's take one more metric space which is complete. Let Y D2 be a complete metric space. Be a complete metric space. Now, if f is a uniform continuous function from A to Y, then f can be uniquely extended to a uniform continuous function g from x to y. Okay. So, if f is uniformly continuous, okay, if f from A to Y is uniformly continuous function. If this f is a uniformly continuous function, then f can be extended to a uniformly continuous function. Then f can be extended uniquely to a uniformly continuous function, to a uniformly continuous function capital F from x to y. So a uniformly extended means that is there is a uniformly continuous function f from x to y such that this f is an extension of small f, such that this f is extension means that f restricted a is this little f. Okay, so this means that when we restrict f to a, it will be f. So in other words, we call this f as the restriction of capital F, and this capital F as it's the extension of small f. It is the extension of small f. Okay. So just a minute, please. Okay. Proof of this theorem. So since closure of is x, so for any point in x, we can find a sequence of points in capital A such that that sequence converges to x. So since A closure is x, therefore for any point x in capital X, there exists a sequence an in capital A such that this an it converges to x. So that means the distance between d1 is the metric on x, so distance between an and x it approaches to 0 as an approach to infinity. So this is given, okay, this one. Now we try to define a capital F from whole space to this. So first we note one thing that this F it maps Cauchy sequence onto Cauchy sequence because of uniform continuity, okay. So let's see that first we prove that we prove that if we have a Cauchy sequence in A, if an is a Cauchy sequence in capital A, then f of an is a Cauchy sequence in y, okay. F is a function from a to y. Okay, to prove this is a Cauchy sequence in capital Y, we must show that for each epsilon positive there is some capital N such that the distance between the terms is less than epsilon, okay. Okay, so let's let epsilon be any positive number, okay. Let epsilon be any positive number. So we can choose delta positive since f is uniform continuous. We can choose delta positive such that distance between the points of x, between the points of A, sorry, so f is a function on A only, distance between x and y is less than delta implies this is a d1 here, this is d2, distance between fx and fy is less than epsilon, where these points x and y they are in A. Okay. A reason because f is uniformly continuous, okay, uniformly continuous. Now it's given that xn is a Cauchy sequence. Now since it's given that an, okay, an हमने choose किया शायद an is a Cauchy sequence, okay. Now since this an is a Cauchy sequence, is a Cauchy sequence in capital A. So for this delta positive, in fact for each epsilon positive I can find some capital N such the distance between the points will be less than that positive number. So that let's choose that positive number, this delta, okay. Then there exists capital N, okay, this one, such that distance between the points of this sequence A and AM is less than delta for all n m greater or equal to for all n m greater or equal to capital N, okay. Now look at this, these points they are in A, okay, these points A and they are in A, and for the points A, X and Y in A, whenever distance between the points is less than delta, then distance between their images will be less than epsilon. So this gives, let's name it star here, okay, this one. So this implies distance between the points f of an is less than epsilon for all n m greater or equal to capital N by star, okay. So thus for each epsilon positive I can find capital N such that distance between f of an and f of am is less than epsilon for all n m greater or equal to capital N, which means that this f of am is a Cauchy sequence in Y. An is a Cauchy sequence in Y, okay. So the uniform continuous mapping, it maps Cauchy sequence onto Cauchy sequence. It is not true for general continuous function, okay. So I can give examples where the continuous mappings doesn't map Cauchy sequence onto Cauchy sequence. This is only true for the uniform continuous mappings. Okay, now we define capital F, okay. We define capital F. This if a point is in A, then we define capital F of x same as small f x, okay. If x is in A, we define capital f of x is equal to small f of x, okay. It's well defined because f is defined on A, okay. If x is in A, then we define this. Now if x is not in A, then how do we define this fx capital F? That's very important, because since our A closure is x, A is not x. So in case A is x, then we have nothing to prove, then there is nothing to prove here if this A is x, okay. So A is not equal to x, A closure is x, okay. So now if the point x is in x, capital X, but not in A, that means x is in A closure but not in A, which means that in that case x will be the limit point, okay. Now second case, if x is in, if x belongs to the set minus A, okay, x minus A, that is, what's this capital X? It's A closure, that's x belongs to A closure but x is not in A. Now as this we have mentioned here, this at the start of the proof, this so for any x in x we can find a sequence an, जो भी x x में होगा आप एक sequence निकाल सकते हो a से, so that an converges to x. So this point is in x, okay. So for this point I can find a sequence in a. I can find a sequence in a. Then so that's this. Then there is a sequence, there exists a sequence xn, n runs from 1 to infinity in a, such that limit of xn is equal to x. So this means the sequence xn is convergence sequence, which means that xn is a convergent sequence, not in a but in a closure. That's is a convergent sequence in a closure, okay. That's equal to x, because this point x is, it's not in a, okay, it's in a closure. So it's convergent sequence in a closure and hence it's Cauchy in a. ये Cauchy sequence में आपको इसका जो लिमिट है ना वो आपको नहीं देखना, आपको सिर्फ इसकी टर्म्स देखनी. Does they converge to each other as n is approaching to infinity, वो आपको देखना. वो हो रहा है because this limit, this the sequence, the limit of the sequence, it's x. So that means the terms of the sequence, they will approach to each other as n is approaching to infinity. So which means that this is a Cauchy sequence. This means xn is a Cauchy sequence, is a Cauchy sequence in capital A, okay. But whenever xn is Cauchy, then its image must be Cauchy in y, which means that f of xn is a Cauchy sequence in capital Y, and y is complete. It is given complete. Y is complete. Therefore f of xn converges in y. So we define f of x, we define a number f of x which is the limit of this, because it converges in y, so this limit exists. Limit f of xn and approaches to infinity. So whenever x is in a, then we take capital Fx to be small fx. If x is not in a, then I can find a sequence xn, and which is a Cauchy sequence in a. So f of xn is a Cauchy in y, and hence it's convergent. So the limit of this f of xn is it exists, and we take this limit to be the value of capital Fx. So in this way we defined capital F for each x in x. But here we must define the well-definedness of this fx, capital F, because actually whenever this x is not in a, it is in a closure. So then we have a sequence xn in a which converges to x. But there may be more than one sequences in capital A which converges to x. एक से ज़्यादा सीक्वेंसेस कैपिटल ए में हो सकती है जो एक्स पर कन्वर्ज करे. एक से ज़्यादा सीक्वेंसेस, हमने सिर्फ एक सीक्वेंस देखी है ना, एक सीक्वेंस के रेस्पेक्ट में आपने इसका लिमिट चेक किया. मे बी देयर मे बी अदर सीक्वेंस, तो उस टाइम आप कैपिटल एफ एक्स का वैल्यू, आप सपोज आपके पास दूसरी सीक्वेंस होगी सी एक्स एंड डैश विच कन्वर्जेस टू एक्स, देन यू मस्ट हैव एफ ऑफ एक्स एंड डैश. देन व्हाट विल बी द लिमिट ऑफ एफ ऑफ एक्स एंड डैश? क्या वो यही कैपिटल एफ एक्स आप लोगे? So that means this limit it depends on actually this sequence जो आपने चूज ऊपर की है x के लिए, और हमें ये इंश्योर करना है इट मस्ट बी इंडिपेंडेंट ऑफ द सीक्वेंस। अगर हमें ये आ जाएगा ना इट, तो आप जहाँ पर कोई भी सीक्वेंस लोगे, सो देन यू कैन डिफाइन एफ ऑफ एक्स दैट लिमिट ऑफ एन अप्रोच टू इनफिनिटी एफ ऑफ एक्स, क्योंकि ये अगर इंडिपेंडेंट होगा ना सीक्वेंस पर, मतलब अगर आपके पास यहाँ पर दो सीक्वेंस होगी विच कन्वर्जेस टू एक्स, आपको प्रूव करना है लिमिट ऑफ कैपिटल एफ एक्स एन इज सेम एज लिमिट ऑफ कैपिटल एफ एक्स एन डैश, दूसरी सीक्वेंस जो आपके पास होगी, तो बोथ द लिमिट्स आर सेम, दैट मीन्स दिस लिमिट, ये जो नीचे आपने लिमिट लिया, इट इज इंडिपेंडेंट ऑफ द सीक्वेंस एक्स एन, so then this f of x will be well defined. So now let us see that this capital F x, it is independent of the sequence x n that we have chosen here. Okay, so next we verify that this is independent of the sequence x n. Now we verify that f of x जो आपने नीचे डिफाइन किया is or does not depend, okay, does not depend on f of x does not depend on the sequence xn, the sequence xn. ओके, अब जैसे जैसे आपके पास ना मैं ये क्यों मेंशन कर रहा हूँ यहाँ पर, बिकॉज यू नो दैट वी हैव अ नंबर 1 एंड वी हैव अ सीक्वेंस 1 by n which converges to this 0, okay, 1 by n it converges to 0, but we have another sequence 1 by n plus 1, this is a different sequence, or 1 by n square you can take, 1 by n square जो sequence होगी, it's not same as 1 by n, and this sequence also converges to 0, okay. तो ये जो लिमिट है आप डिफरेंट सीक्वेंसेस ले रहे हो और लिमिट 0 आ रहा है। अब मसला है कि इमेजेस पर क्या होगा, क्या इमेजेस भी एक ही लिमिट पर कन्वर्ज होगी, वो आपको चेक करना, वही हम वेरीफाई करने जा रहे हैं। अगर आप यहाँ पर डिफरेंट सीक्वेंसेस भी लोगे, स्टिल द इमेजेस ऑफ दोज सीक्वेंसेस दे विल कन्वर्ज टू द सेम पॉइंट, that means this point is independent of those sequences. अब 10 sequences लो या 20, the limit will always be the same. वही मैंने यहाँ पर, now we verify that f of x does not depend on the sequence xn. So for this we take another sequence yn which converges to x, okay. So let yn be a sequence, let yn be a sequence in A such that limit n approach to infinity of yn is equal to x, okay. So limit is same. अब आपको प्रूव करना इमेज का लिमिट भी सेम रहेगा। we show that this we show limit of f of xn is same as limit of f of y, and they are equal to capital Fx. ये तो आपने लिया ही ऑलरेडी कैपिटल Fx, अब ये भी आपको प्रूव करना है ये कैपिटल Fx है, इट्स कैपिटल Fx. Now a limit of xn is same as limit of yn, that means distance between xn and yn is that approach to 0. So we have distance between xn and yn, it approaches to 0 as n approach to infinity. Okay, so this distance is approaching to 0, okay, this one. So which means that therefore there exists some capital N greater or equal to 1 such that distance between xn and yn is less than delta for all n greater or equal to capital N. Okay, but now from uniform continuity it means that distance between f of xn f of yn is less than epsilon for all n greater or equal to capital N. So which means that limit of f of xn is same as limit of f of yn, or you can see this limit of f of y is equal to f of x. You can find the distance between these two, so you will see that this distance will be the same. So let's calculate that distance. Can calculate the distance between limit of f of yn and f of x. Okay, so that distance will be f of yn f of xn. Okay, limit of f of xn is fx, that is already taken. This limit is f of x. Okay, ये आपने पहले लिया है. This is f of x. So this means distance between, let's find this distance, f of yn and f of x. So we can apply triangle inequality here. It is distance between f of yn f of xn plus distance between f of xn and f of x. So this thing is less than epsilon, and this is also, this can also make this less than epsilon. Okay, because limit of f of xn is capital Fx. Okay, so this means it's less than, say, twice epsilon for all n greater or equal to capital N. So that means limit of f of y is also f of x. So limit is the same, which is equal to limit of f of x. Okay, so in this therefore this f is well defined. F is therefore f from x to y. Okay, let's write it precisely here. F from x to y is well defined. F from x to y is well defined, and obviously f of x is equal to small f of x for all x in a, क्योंकि आपने इसको define ऐसे किया, whenever x is in a, capital f x is equal to small f x. So that is f is an extension of small f x. That's capital F is an extension of small f. अब सिर्फ आपको चेक करना है कि ये जो कैपिटल F है, इट्स यूनिफॉर्म कंटिन्यूअस. इट इज यूनिफॉर्म continuous. Now we show that this capital F is uniformly continuous. Okay, this mapping is uniformly continuous. So let's again choose any epsilon positive given any epsilon positive. Okay, we can find delta positive. Choose delta positive such that, because this f is uniform continuous, small f is uniform continuous and small a, so we have this. Choose delta positive such that distance between x and y is less than delta implies distance between their images under small f. So this is a given because f is uniform continuous where the points x and y they are in a. और ये पहले आप लिख सकते हो यहाँ पर. Let's write it here. It's better to write it here. Such that for all xy in A, d1 xy less than delta implies d2 fx fy less than epsilon. Okay, so instead of epsilon, let's write epsilon by 3. Okay, so read it. I want to ensure the same property for whole space X actually, okay, for the mapping capital F. So let us choose any 2 points in whole space. Let A and B, they are the any 2 points of X, okay. Then as earlier, I can find a sequence an, then an for the point A I can choose a sequence A, and for the point B I can choose a sequence B and C. Then there exist sequences an and bn in capital A such that limit of an is equal to small a, limit of bn is equal to small b, and this limit of f of an is equal to capital F of a, limit of f of bn is equal to capital F of b, capital F of b. So from this I can choose a point for this particular, for this here delta 1, okay, choose delta 1 positive, this is delta 1. So since the limit of an is a and limit of an is f of a, so for delta 1 I can find a point, which is in the open sphere having radius a, having center a and radius delta 1, and similarly I can find a point in the sphere, in the open sphere, with radius say epsilon and center at f of e. So because actually ये जो है ना f of a की definition से आ रहा है, ये f of a n, limit of f of a n is equal to f of a. So for every epsilon positive I can so this limit, अगर आपको लिमिट की डेफिनेशन याद होगी, लिमिट की डेफिनेशन क्या है मीट्रिक स्पेस में, when we say x and converges to x, it means that for all epsilon positive I can find a capital N such that this xn, it belongs to the sphere as epsilon with center at x for all n greater or equal to capital N. This is the definition of convergence of limit in metric space actually. Okay. Or you can say distance between xn and x is less than epsilon, for all n greater or equal to capital N. So let's apply this part, this form of the definition. Distance between xn and x is less than epsilon for all n greater or equal to capital N whenever limit of xn is a. So same thing can be applied here. So that means I can choose. So let's write it here. So therefore we can choose up 2 points x and let's choose 2 points x and y. So therefore we can choose x and y in obviously in capital A. Therefore we can choose therefore we can choose xy in capital A such that distance between t1, distance between the point x and A, let's take this as, let's choose that epsilon as delta 1 by 3 here, positive number, and distance between y and B, the second point is B here in x, so this is less than delta 1 by 3 and this. Now next one, distance, this is here d2, distance between f of x, you can take it as capital Fx as, because small fx and capital Fx is same whenever x is in a, here x is in a, x and y is in a. So small f of x and capital f of a. So let's choose the positive number here, epsilon by 3. And the fourth one is distance between this is here f of y and capital F of b. This is less than epsilon by 3. This is less than epsilon by 3. Name it 1. Okay, this is 1. This is simple because A is Denison. A is Denison X, and this the very definition of capital F of X, जो आपने F of X को define किया ना, तो उसकी definition से ये आ जाएगा जो second आपने लिखा d2fx capital F less than epsilon by 3, d2f capital F be less than epsilon by 3. So now let's see the distance, because we have to apply this part actually. We apply आपने जो points यहाँ पर choose किए ना, x and y. You will prove that distance between these 2 points is less than delta 1, so that you can apply this one, this star. Okay, let's name it 2 here. Okay, let's first name it 2 here and name this one as 1. Now let's find the distance between x and y. That's obviously less than delta 1. You can easily verify it by applying triangle inequality. And distance between a and b. So assume that the distance between the points a and b is less than delta 1. Okay, so we need to show that our delta 1 by 3 of distance between a and b is less than delta 1 by 3, and we show that distance between fa and fb is less than epsilon. So assume distance between a and b is less than delta 1 by 3. तो f फंक्शन है कैपिटल x से लेकर कैपिटल y तक. आपने यहाँ पर 2 पॉइंट्स लिए जिनके दरमियान डिस्टेंस लेस देन डेल्टा 1 by 3 है. You will prove that the distance between their images is less than epsilon. Okay. Now let's see this distance between x and y. What's this distance? By triangle inequality, it's less or equal to distance between x and a plus distance between a and b plus distance between b and y, and everything is less than delta 1 by 3. So this is less than delta 1 by 3 plus delta 1 by 3 plus delta 1 by 3, which is equal to delta 1. And whenever distance between x and y is less than delta 1 and x and y, they are the points in a, it means that distance between their images under small f, this is less than epsilon by 3. Okay, by 1. Okay, name it third now. Name it third. So finally we see the distance between distance between fa and fb, that we want to less than epsilon, that distance. So we have to apply the triangle inequality here. We have to apply triangle inequality here. It is distance between fx and fa. So this is less or equal to distance between fa fx plus distance between fx fy plus distance between fy fb. Okay, this one. And since distance between x and y is less than delta 1, so this it means that distance between f2x and distance between capital Fx and capital Fy, it will be less than epsilon by 3, because capital F and capital Fx and capital Fy, they are small fx and small fx and small fy, because x and y, they are in A. And this is less than epsilon by 3. This is also less than epsilon by 3, because x and y are chosen in such a way that distance between fa and fx is less than epsilon by 3, and distance between fy and fb is less than epsilon by 3. So everything is less than epsilon by 3 on the right hand side. Whenever x and y, distance between x and y is less than delta 1, that's here. So we apply this second and third. Actually, we apply second and third. So this is less than epsilon by 3 plus epsilon by 3 plus epsilon by 3 by second and third. And note that this thing, and note that capital Fx is same as small fx, because this small fx, this x and y, they are in A, and on A, capital F and small f, they are same. It's epsilon by 3. So that means distance between Fa and Fp is less than epsilon. So thus, for all epsilon positive, there exists delta 1 positive, such that distance between AB less than delta 1 by 3 implies distance between FA FB is less than epsilon. So hence F is uniformly continuous. Hence F is uniformly continuous. Hence F is uniformly continuous. So this capital F is unique. You will verify it yourself. So home assignment, prove that the mapping capital F that you had defined above is